In this video, we're going to explore equations of lines and planes in 3 dimensions. We know from yesterday that if I have these two vectors, and if I do the cross product, and the cross product is 0, then we know that those two vectors are parallel. Now, if we look at their magnitudes, the magnitude of one and the magnitude of the other are multiples of each other. So we know if the two vectors are parallel, if they're parallel, then their magnitudes must be multiples of each other. In particular, this number k must be the magnitude of one over the other, and it doesn't matter which direction you go. It could have been the magnitude of v over u, or the magnitude of u over v. It doesn't matter. If they are in opposite directions, then I must have a multiple that it's between them must be negative. Now we're going to use this information to find equations through a given point given a certain direction. So if we have a point, which is the point P, and we're going to let this vector v be a, b, and c. Then for any point on the line Q, we know that from P to Q will be parallel to v. And as we've discussed before, we have a scalar, we're going to call it t. We used a k, now we're going to call it t. Such that if I take the vector from P to Q, it should equal the vector v by some multiple of t. Now to find the vector P to Q, I take my ending point, which is Q, subtract off my beginning point, which is the P point, and so x minus x naught, y minus y naught, and z minus z naught would equal my vector v multiplied by that scalar value, which is t. And I get this. Graphically, this is what I'm doing. If I use my regular vector operations, then I distribute in my t, my scalar, onto my v vector. And if I undo the subtraction of each one of these, which is perfectly allowable, we have our vector, which has the ending point of x, y, and z. Subtracting off our vector that has the ending point x naught, y naught, and z naught, it should be equal to my polar's on my mind. My parametric t, my scalar, I already let the cat out of the bag, it's parametric, whatever, multiplied by my components. So moving this vector to the other side, which again is perfectly legal, I'm going to get this vector x, y, and z is going to be equal to the vector formed with x naught, y naught, and z naught plus this t multiplied by the vector a, b, and c. If we let r be our vector x, y, and z, and r naught equal our vector x naught, y naught, and z naught, we get this, just to make it kind of look nicer. Now, I know if the vectors are equal, then my x minus x naught must be equal to the t to a. So x minus x naught must be equal to the t a, y minus y naught must be equal to the t b, and the z minus z naught must be equal to the t c. Solving for each variable, we're going to get x is equal to x naught plus ta, y is going to be y naught plus tb, and z is equal to z naught plus tc. If we solve for t in each one of these equations, we get x minus x naught over a, y minus y naught over b, and z minus z naught over c, and each one of these equal t, but t is equal to t all day long. So the symmetric equation of a line is x minus x naught over a, y minus y naught over b, and z minus z naught over c. That brings us to our first theorem in this section. It says a line L parallel to this vector and passing through this point can be described by the following parametric equations. X is equal to x naught plus ta, y is equal to y naught plus tb, and z is equal to z naught plus tc. If the constants a, b, and c are non-zero, then L, my line L, can be described by this symmetric equation of a line. X minus x naught over a, y minus y naught over b, and z minus z naught over c. They want me to find the parametric and symmetric equations of the line L through these two given points. So I first need to find the vector v that can be described from the point P to Q. So v is equal to, and we do our usual 2 minus 4, 3 minus 0, 5 minus 1, which gives me -2, 3, and -4. Now we use the fact that our vector r is equal to the vector r naught plus t multiplied by our vector v. And we know that our r naught can be described as 4, 0, and 5 plus some t, and then we found our vector, which is -2, 3, and -4. So we know that r is the vector x, y, and z, which is equal to 4, 0, and 5, plus -2t, 3t, -4t. All I did there is multiply the scalar in. We know that x has to equal 4 minus 2t, y has to equal 0 plus 3t, and z has to equal 5 minus 4t. Where this is coming from is 4 minus 2t, 0 plus 3t, and 5 minus 4t. So there are my parametric equations of the line, assuming t is a real number. So there's my parametric equations of a line. To find the symmetric equations of the line, I'm going to need to solve for each one of those and solve for t. So for my first one, I have x minus 4 is equal to -2t. So x minus 4 divided by -2 is equal to t. I have y divided by 3 is equal to t. And then my last one is I have z minus 5 is equal to -4t. So z minus 5 divided by -4 is equal to t. Now I know with my my symmetric equations, x minus 4 divided by 2 must be equal to y over 3, which must be equal to z minus 5 divided by -4. And now I found my symmetric equation, and I have found my parametric equation that both describes the line that goes through those 2 points. Now what they're giving me is a point and vector. I want to find a parametric equation of the line through that point with the same direction. So I want a parallel vector. I'm going to use the fact that to find a parallel vector, I have to have some p and q, and it's going to be equal to some t multiplied by my vector v. So the way I would find p, well, given to me, and I'm going to just say q must be the point x, y, and z. So, like I did before, to find my vector, I know the vector from p to q must be x minus 3, y minus 1, and z minus 5. Now that's nothing we haven't done before in our first finding vectors in 3 space, right, if you're given 2 points. And this is going to be equal to some t being a scalar multiplied by my vector v. Now, this looks an awful lot like what we had up above with a parametric equation, and the fact that we can, of course, break this out as the vector x, y, and z using the way that vectors behave, and then minus 3, 1, and 5 is equal to t, 1, 1, and 1. Just moving that 3, 1, and 5 to the other side, that vector to the other side, x, y, and z is going to be equal to 3, 1, and 5 plus my scalar multiplied by my other vector. Now I'm going to do the parametric equations like I did up above. So my parametric equation is x is going to be 3 plus t, y is going to be equal to 1 plus t, and z is going to be equal to 5 plus t. So I found my parametric equations. And I'm really bad at this, but the assumption is that t is always coming from the real numbers. Okay, so I have my parametric equations of the line through the point in the same direction. And what I want to know now is, where does this line intersect with the xy plane? Now remember, when we're on the xy plane, z must be equal to 0. So if z is equal to 0, then I'm going to go to my z here and say, well, z has to equal 0. So z is equal to 5 plus t, plus, and I want to make that a t, 5 plus t, but this also equals 0. What I'm doing now is I'm finding the t value in which this is going to give me the ordered triplet where this line is going to cross the xy plane. So I end up with t equaling -5. I now put that t into my other two equations. So x is equal to 3 minus t, which is 5. So x must equal -2. Y must equal 1 minus 5. So this gives me -4. So the location of where this line is going to cross the xy plane is at -2, -4, and 0. There's going to be times in which we only want a portion of the vector. We just want a part of the line. And so what we do is we use these adjusted equations. X is equal to x naught plus t, x1 minus x naught, and then etc. for t between 0 and 1. So this allows me to take just a portion of the line between the two given points. So of course, we know at this point we have r, our vector r, is equal to r naught, vector r naught, plus t, and then the line p to q. So we know that r is equal to the 4, 0, and 5 plus t multiplied by -2, 3, and -4. And you're thinking, what? Well, these are the same points we used up above. Not this example, but this example. So these are the same numbers. That's how come I was able to quickly get that other vector. Same example, or same numbers. Okay, so from there we know that x must be equal to 4 minus 2t. Y must be equal to 3t. And z must be equal to 5 minus 4t. 4t, this time we're in the interval between 0 and 1. And if you're thinking, didn't we just find that? Yes, we did. But this time my t is not all real numbers. T is in a specific interval. We can also find the distance between a point and a line. In two-dimension, we'd say let L be a line in the plane and let M be any point not on the line. Then we define the distance from M to L as the length of the line segment from M to P, where P is a point on the line such that the distance, or that line segment from M to P is perpendicular to L. Bam. In 3 space, there's really no clear way to know which point on the line creates a perpendicular line segment. So what we do is we select an arbitrary point on the line, and then we use the properties of vectors to calculate the distance. So let P be an arbitrary point on the line, and let V be a directional vector for L. That means it's going in the same direction. By the area of a parallelogram, which we learned last section, the vectors P, M, and V form two sides of parallelogram with the area given by the cross product. Using the formula from geometry, the area of the parallelogram can also be calculated as a product of its base times its height. So we now have a formula in 3 dimensions for the distance. In this example, we're going to find the distance from point A and the symmetric equations of the line. So we've got this line, they're giving me the symmetric equations. So I'm just going to rewrite the symmetric equations in a form that's a little bit easier to pull information off of. We have x over 1 is equal to y over negative 1, which is equal to z over negative 1. Now, any point on the line, I can choose any point on the line. The best point on a line, for this one, it would be the point 0, 0, and 0. The reason that is a really good choice, and I know it's on the line, is because it satisfies this. If x equals 0, y has to equal 0, and z has to equal 0. If there were other things going on here, I wouldn't have been able to pick this point, but this point I know satisfies this symmetric equation of a line. It has to satisfy it when you pick a point. This is a nice point to pick. Now, we also know the vector v is 1, negative 1, and negative 1. That's in the same direction as the line L. And that comes from our symmetric equation, 1, negative 1, negative 1. To find my distance, then, this is going to be my magnitude of the cross product from P to A, crossed with V, so that magnitude, divided by the magnitude of V. So, because I chose a really nice P, my point from P to A is going to be the cross product. So let's do the cross product of P to A, crossed with V. This is going to be the cross product of negative 3, 1, and 1. And that's because I chose a nice P. And then that's going to be crossed with my V, which is 1, negative 1, and negative 1. I do my regular cross product like I did in my last section. And I end up with 0, negative 2, and 2. So I'm going to go back and find the magnitude of this. The magnitude of this cross product is going to be the square root of 0 squared plus 4 divided by my magnitude of V. My magnitude of V is going to be 1 plus 1 plus 1. So I end up with the square root of 8 over the square root of 3. And I can clean that up if I want. I can write this as 2, the square root of 2 over the square root of 3, or I can write it as 2 over the square root times the square root of 6 over 3. I'm actually okay if you leave it like this. You don't have to do anything fancy. I'm fine with that. Now, let's find the distance from the point A to the parametric equations x is equal to negative 1 minus t, y is equal to negative t, and z is equal to 2. This one's slightly different. So the first thing I'm going to do is write it in symmetric form. And that allows me to find the vector v that I need. So to write it in symmetric form, I'm going to solve for t. So my first one, I'm going to have x plus 1 is equal to negative t. So x plus 1 divided by negative 1 is equal to t. For y, that one's actually not too bad. Y is equal to negative t. Y over negative 1 is equal to t. The last one's a little different. I don't have a t for that one. I have z is equal to 2. And it doesn't have the parameter t. So if you notice what's been happening when I've been pulling these vectors, and you're like, where are these vectors coming from? And that goes back to the way that we did this in the beginning. We would have had that multiplier on t would have been my divisor. That multiplier on t would have been the vector I started out with. Since this doesn't have a parameter here, that means that I must have had 0 for that part of my vector. So the vector then that is formed v is going to be the vector that is -1, -1, and 0. Now, what I want to do then is pick a point P that must be on this line. And for this to work out, I have to find the point P. The point P must satisfy x plus 1 divided by -1 and y divided by -1. That has to be satisfied. And one of the ones that would satisfy it is if I had x is equal to -1. I could have chose x is equal to 2. That would have been fine too. But I always go with the easiest if I can. So if x equals -1, then y would have to be 0 to be satisfying this equation. So the point P that I'm going to choose is -1, 0, and z is 2, regardless of what I want to do. So that's my point P. I have my vector v and I have my point P. So I now need to find my P to A. There's my A, there's my P, so I need to find this vector. So it's going to be 4 minus -1, so that's going to be 5. And then it's going to be the 2 minus 0, which is 2. And then 5 minus 2, which is 3. So that is my vector P. I have to find the cross product. P crossed with A, crossed with V. And then I also have to find the magnitude of that. And then I have to find the magnitude of V. So I would find P, the vector PA crossed with V. And I end up with 3, -3, -3. So then my magnitude is going to be the square root of, 3 times 9 in the numerator. And then in the denominator, I'm going to have the square root of 2. Then my answer is going to be 3 root 3 over the square root of 2. And that's my distance between that point and that line described by those parametric equations. Let's talk about two lines in 3 dimensions. If I have 2 lines in 3 dimensions, then they could be parallel. They could be the same line. They could be skewed, which means they're not parallel, but they're not intersecting either. They could be perpendicular. So we have a lot more options. How do we decide? Well, we look at the direction vectors, and we also look to see if they share a common point. If their direction vectors are parallel and they share a common point, they are the exact same line. If their direction vectors are parallel and they don't share a common point, then they're parallel but not equal. If their direction vectors are not parallel and they share a common point, then they're intersecting. If their direction vectors are parallel and they don't have a common point, then they're skewed. So let's determine if these lines are parallel. And if they are parallel, find the distance between them. So the first thing I'm going to do is find the direction vectors, which means I need to write these in the symmetric form. So I'm going to take my line 1. I'm going to work with line 1 first. Here's line 1. And I'm going to write their direction vectors. So I'm going to put it in the symmetric form. X minus 1 divided by 1 is equal to t. And y divided by 1 is equal to t. And z minus 2 divided by 1 is equal to t. Now, we know that these denominators, when it's in this form, because t is equal, these are all equals, that means that if I write it as x minus 1 divided by 1 must equal y divided by 1, which must equal z minus 2 divided by 1. Those denominators are my direction vector. So my direction vector v1 would be 1, 1, and 1. I need to find a point that's on this line. So I need to find a point that satisfies all of these. So I have to find a point that's going to satisfy x minus 1, which has to equal y, which has to equal z minus 2. So let's just pick the easiest one, which is x is equal to 1. If x is equal to 1, then the point I'm going to have is 1. If x is 1, 1 minus 1 is 0, so that y must be 0. And then this z minus 2 has to equal 0, which equals this, the numerator. All these numerators have to be equal. So that means my point has to have a 2 for the z. Now let's do the same thing with our second line, so L2. So L2, I have these. Oh, well, that's kind of nice. They're telling me that I have t is equal to. So that's already actually really nice. That already, because they have them set equal to each other, that means we have the symmetric equation of a line, which means all I have to do then is write x minus 3 over 1 is equal to y minus 1 over 1, which is equal to z minus 3 over 1. And its direction vector, v2, must be the point 1, 1, and 1. So that's really nice. Because the vectors are the same, my directional vectors of 1 and 2 are the same, we know these lines L1, L1, and L2 are parallel. So now I got to figure out what the distance is between these 2 points. So I have to find some point, I'm going to call it P2, this is P1 up here, that is on this second line. I'm going to go with my easiest one to make, this time I'm going to make y equals 0, or if I chose 1 for y, that means I would have x minus 3 would equal to 0, and z minus 3 was equal to 0. So I end up with 3, 1, and 3. I could have used anything, by the way. I could have used x is equal to 1, and that could have worked too. So if I would have chose, by the way, as long as it's just a point on there, if I had said x is equal to 1, then I would have had 2 is equal to y minus 1, and I would have had 2 is equal to z minus 3. So as long as you pick one point on there, it doesn't matter which point you pick. Okay, so now I need to find the distance from point 2 to point 1. So I need to find the point 2 to point 1. So this vector will be the 3 minus 1, the 1 minus 0, and the 3 minus 2. This gives me 2, 1, and 1. Nice vector. Now I'm going to do the cross product of P2 and P1 with V1 or V2 because they're the same thing, so it won't matter. And when I do that cross product, I'm going to get the vector 0, 1, and negative 1. Positive 1. Sorry about that. Okay, so the magnitude of P2 and P1 crossed with V1 is going to be 1 plus 1, so that's nice. The magnitude of V1, or V2, because they're the same thing, is going to be the square root of 3, because I have 1 plus 1 plus 1. So my distance is going to be the magnitude from P2 to P1 crossed with V1, which is the same thing as V2, divided by the V1, magnitude of V1, which is going to be, my final answer is going to be the square root of 2 over the square root of 3. Now I'm going to be asked to find if my lines are parallel, equal, parallel and not equal, perpendicular, or skewed. So remember, perpendicular, I would do the dot product. Parallel is always the cross product. So the first thing I'm going to do, take my line 1, and I'm going to write it with the symmetric form. So I'm going to add 1 to both sides and divide by 2. So x plus 1 divided by 2, which is equal to t. Similarly, on this one, I'm going to do the y minus 1 divided by 3. And then my last one is going to be z divided by 7. So my directional vector, v1, is going to be 2, 3, and 7. So I'm going to do the same thing with line 2. Oh, look at that. Line 2 is already set up for me. That's kind of nice. So I have x minus 1 over 1 is equal to 2y. Actually, I need to take that multiplier and put it in the denominator. So it's going to be y minus 4 divided by 3 halves. And then it's going to be equal to, I have to do the same kind of thing here. So I have to get that 2/7 in the denominator. So that means I need to factor out 2/7 off of that negative 2. And so I'm going to have z minus 7 divided by 7 halves. Now, just as a reminder, I needed to have a z plus or minus a number. So I factored out, so in other words, I divided both of this term and this term by the 7 over 2. And when I divided by the 7 over 2, I got z minus 7 over 7 over 2. Okay. So my v2 is going to be equal to 1, 3 halves, and 7 halves. Okay. So if I factor out a v2, I factor out a 1/2. If I factor out 1/2, I'm going to get 2, 3, and 7, which is the same directional vector as my v1. So these are parallel. To see if they're equal, I'm going to let t equals 0 for the first line. So if t equals 0 for this first line, I'm going to get x is equal to negative 1, y is equal to 1, and z is equal to 0. And this point will be on the line 1, which is negative 1, 1, and 0. So now I need to check whether or not that satisfies my other set of equations for my line. So if I put negative 1 minus 1, does that equal 2/3, 1 minus 4? And then does that also equal at the same time 2/7 multiplied by 0 and then minus 2? Well, this gives me a negative 2, so that tells me that these two are equal because 2 times 0 is 0. So we have that equality because this is going to be negative 2, 0 minus 2, so those two. So now I just have to check to see if that gives me negative 2. So 1 minus 4 is negative 3. Negative 3 times 2/3 is negative 2. Oh, so that point, which happens to be on my first line, is also on my second line. So that tells me that they're parallel and equal. Okay. Take a look at my next one. So I'm going to be looking at my line 1 and line 2, and it's already nicely put into the symmetric form. We love it when it's in symmetric form. So I can just write line 1, x over 1 is equal to y minus 1 over 1, which is equal to negative z over 1. So my directional vector v1 is going to be 1, 1, and 1. My line 2 is going to be x minus 2 over 1, and then y over negative 1, and then z over 2. So it is 1, negative 1, and 2. Now there's no way I can make one to be the other. It's just, I'm not going to be able to do a multiplier of a scalar times v2 to get v1 and vice versa. It's just not going to happen. So we know that these are not parallel. So not parallel. Now we have to do is see whether or not they intersect. To do this, I'm going to start with one of the two lines. Doesn't matter which line. I'm going to start with my first line, and I know that x is equal to y minus 1, which is equal to negative z. Let's just equal to some other random variable. Let's choose a. Don't want to use m, that's slopes. A is okay. So from this, we know that x is equal to a, y minus 1 is equal to a, and negative z is equal to a. Then if I take this one and I have y is equal to a plus 1 and z is equal to negative a, I can plug this back into the second equation and see whether or not this holds true. So for wherever I see x, I'm going to replace it with a on the second equation. So a minus 2 over 1. Does that equal? And then I'm going to put in the y replacement, which is a plus 1 over negative 1. And then does that equal my z replacement, which is negative a over 2. So let's take a look at just these first two right here. These have to be equivalent, so let's see what we get for a. I'm going to bring this negative up here. So it's over 1. So I have a minus 2 is equal to negative a minus 1. All I did was pull the negative up in the numerator. So I'm going to add a to both sides. So I get 2a. I'm going to add 2 to both sides, and so I get positive 1. So I get a is equal to 1/2. Now simultaneously, this also has to hold true. So I have negative a minus 1 is equal to negative a. Well, when I try to solve this one, I'm going to get, adding a to both sides, I'm going to get negative 1 is equal to 0. So that isn't going to work. So because they don't work, we know that this has no solution for a. A is not going to have any solution, which tells me that these two lines are not parallel, but they're also not crossing, so they're skewed. Let's take a look at how we can build an equation for a plane. We've been working on with lines, now we're going to work with the equation of a plane. So we know from linear algebra that one vector with at least one non-zero component will give you a line. Two linearly independent vectors, each with at least 2 components from R, will give you R2. 3 linearly independent vectors, each with at least 3 components from the real numbers, will give you R3, and etc. This means we need 2 linearly independent lines, 2 distinct lines, that intersect to describe a plane. Or we need a line and a point not on the line to describe the plane. The reason this is if you were to think about 2 vectors that are orthogonal, and you were to just twist the one that's straight up, and as you're twisting it and spinning it, you are going to get a plane from that spinning. The faster you spin it, that top, if you will, it seems to form that plane. So we're going to let n, this vector n, be a vector and p be some point. Then the set of all points q will equal x, y, and z such that p to q is orthogonal to n, and it forms a plane. We see that n is a normal vector or perpendicular to the plane. Remember, the dot product of orthogonal vectors is 0. This fact generates the equation of a plane that n, the vector n, and the dot product from p to q is equal to 0. If we rewrite this, we end up with this. A, x minus x naught, plus b, y minus y naught, plus c, z minus z naught, which is equal to 0. So if we are given a point and some vector n that is normal, a vector n, that is normal, then the equation is described as the scalar equation of a plane, where I have a, x minus x naught, b, y minus y naught. And the a, b, and c is coming from the components of the vector. The x naught is coming from the points, or the values for the ordered triplet from the point. And the x's are just x, y, and z. This is where we start to see equations of lines like we're familiar with 2x minus 3y plus 2z is equal to 5. Okay, that's where this is coming from. Now this is the scalar equation of a plane, and then the general form of a plane is ax plus by plus cz plus d is equal to 0. So we're going to find the general equation of a plane passing through these 3 points. So what I'm going to do is I'm going to find the vector that can be described from P to Q and Q to R. I could have easily have done from P to R too. It doesn't really matter. So let's do P to Q first. Now you're going to get, like, I got this in my sleep. So 2 minus 1, which gives me 1, 4 minus 1, which gives me 3, and 3 minus 1, which gives me 2. So that's my first vector. From Q to R is my second vector, and it's going to be negative 1 minus 2 is going to give me negative 3. Negative 2 minus 4 is going to give me negative 6. And negative 1 minus 3 is going to give me negative 4. So there's my second vector. To find the vector n, our vector n, which is going to be orthogonal to both P and Q, we know it's going to be the vector formed with the cross product from P to Q and Q to R. When I do this cross product, I'm going to get the 0 times 1 minus 2 times j plus 3 times k. Now I'm going to choose one of the points. I don't care which point it is. I'm going to choose the point that's got the least amount of work. So I'm going to choose this point right here. And I'm going to put all the information here. P naught is 1, y naught is 1, z naught is 1, a is the 0, b is the negative 2, and c is the 3. So my equation is going to be 0, that's my a, x minus my x naught, which is 1, plus b, which is negative 2, y minus y naught, which is 1, plus 3 multiplied by z minus z naught, which is 1, and this equals 0. So this is the scalar equation of a plane. To find the general form of a plane, I'm going to have 0 minus 2y plus 2 plus 3z minus 3 is equal to 0. So negative 2y plus z, 3z, excuse me, plus minus 1 is equal to 0. So that is the general form of the plane through those 3 points. I'm going to find the parametric equation of the line that passes through this point and that is perpendicular to the plane of the equation, given to me as 2x minus 3y plus z is equal to 7. We know from our previous sections that if we pull off the coefficients, 2, negative 3, and 1, that'll give us our normal vector. And in fact, we get it from here as well. The normal vector is the coefficients. So a vector normal to this plane, n, is going to be the coefficients 2, negative 3, and 1. So that is my normal vector. So I'm going to find another vector, P to Q. P to Q. I don't have a Q, so I can always say Q must be x, y, and z. So from P to Q must be the point from x plus 2, y minus 1, and z minus 3. Now this vector P to Q, because it has to be parallel to the plane, or excuse me, perpendicular to the plane, that means it's running parallel to this normal vector. So we know from above that PQ, the vector PQ, must be equal to t multiplied by some vector n, which is our normal vector. So we know that x plus 2, y minus 1, and z minus 3, this vector must be equal to 2t negative 3t, and t. So what we get then is x plus 2 is equal to 2t, y minus 1 is equal to negative 3t, and z minus 3 is equal to t. So my parametric equations is x is equal to negative 2 plus 2t, y is equal to 1 minus 3t, and z is equal to 3 plus t. 3 plus t. T is a real number, and there is my parametric equation of the line passing through that point and perpendicular to the plane of the equation given by the equation 2x minus 3y plus c is equal to 7. Whew, okay. Now we're going to look at the distance between a plane and a point. The distance between a plane and the point is defined as the projection of PQ onto N, which is also the absolute value of the scalar projection of PQ onto N, which is the absolute value of this dot product divided by the magnitude of my normal vector. So let's find the distance from this point to the plane who's described by the equation 3x minus y plus 2z is minus 6 is equal to 0. Now we know that the normal vector is going to be the coefficients, so 3, negative 1, and 2. We're going to pick any point on this plane, so let's pick when x and y is equal to 0, or when the y and z is equal to 0. So if y equals 0 and z is equal to 0, I'd have the equation 3x is equal to 6. So x would equal to 2. So I know this is on the plane. So my point Q is going to be the point 2, 0, and 0. Now I could have yet used 0, 0 for x and 0 for y, and I could have gotten z is equal to 3. I could have used either one. It doesn't really matter. What I want to do is find the vector formed from Q to P. So from Q to P. This is going to be equal to 2 minus 1, which is 1, 0 minus 5, which is negative 5, and 0 minus negative 4, which is positive 4. Now I'm going to do the dot product of that vector and N. So 1, negative 5, 4, dotted with 3, negative 1, and 2. So I'm finding this part. I'm going to take the absolute value of that answer. So this is going to equal negative 16. I'm going to take the absolute value of that. I also need to find the magnitude of n. So I'll find the magnitude of n. This is going to be equal to, my n was, so it'll be the square root of 9 plus 1 plus 4, which gives me the square root of 14. So my distance is equal to the absolute value of the dot product, so that'd be 16, over my magnitude of n, which is the square root of 14. So there's that. All right, I want to talk about parallel and intersecting planes. So when we have two planes, they either intersect or they don't. Really, that's it. If they don't, that means they're parallel or they're the same plane. It's really kind of nice. So as an example, we have this plane and this plane. They're crossing in one line. So when they intersect, two planes intersect, it's going to intersect as a line. If they don't intersect, they're running parallel or they're the exact same line. So you have an infinite number of solutions, but in this case, the solution is a line. If we want to determine the angle between two planes, assuming they're not parallel or the exact same line, then we look at their normal vectors. When we look at their normal vectors, then the cosine of my angle is the dot product of the two normal vectors divided by the magnitude of the two normal vectors. Now I take the absolute value of these two, of the dot product. So I'm trying to decide if these planes are parallel, orthogonal, or neither. And if they're neither parallel nor orthogonal, we're going to find the measure of the angle between the two planes to the nearest degree. So I'm going to look at my normals. So I'm going to call this line 1, L1, and I'm going to call this line 2, L2. The normal for the first line is going to be 5, -3, and 1. My normal for my second line is going to be 1, 4, and 7. We can tell by inspection that there is no t, so that if I multiply one vector by the scalar, I'm going to get the other vector. So then I'm going to look to see if they are orthogonal. So I'm going to do the dot product of n1 and n2. When I do this dot product, I'm going to get 5, and then -12 plus 7, which is equal to 0. Oh, these planes are parallel. All right, excuse me, perpendicular. Perpendicular. These planes are perpendicular. So the angle between them, of course, is 90 degrees, or pi over 2. Take a look at my next example here. So once again, I'll look at my normal vectors. Normal for the first one is 1, -5, and -5. My normal for my second line is going to be 5, -5, and -5. Now, if I were to take this and multiply it by 5, I would get this. So these are parallel. Take a look at my last example. Once again, I'm going to look at my normal vector, which is 1, -3, and 6. My other normal vector is 5, 1, and -1. And I can tell you that these are going to be linearly independent. There's no way I can get from one to the other. And you can check it yourself. Since I can't get from one to the other, that means that they are not parallel. So we're going to check to see if they're perpendicular. So I'm going to do the dot product. When I do the dot product, I actually get -4. So they're not perpendicular. So if they're not perpendicular, when they're not parallel, we're going to have to figure out the angle between them. So I go back to the cosine of theta is equal to the absolute value of the dot product, which we know is going to be 4, divided by the magnitude of each one of these. So the magnitude of the first one, which is 1 plus 9 plus 36. Magnitude of the second one is 25 plus 1 plus 1. So my angle theta is equal to the cosine inverse of 4 divided by the square root of 1242. So that gives me an angle that's approximately equal to 83 degrees. So that is the angle between those two planes. So we're going to do one more run at the distance between a point and a plane. The distance between a point and a plane can be described where the plane is in the general form, can be found as d is equal to x naught is the points, a are these numbers here. So the first thing we need to do before we get all Johnny about finding the distance, let me erase that, is I have to find a point on one of those two lines. Doesn't matter which line, I'm going to choose any point. So let's choose the point that satisfies this solution. If y is equal to 0 and z is equal to 0, that means x must equal 1. So I know that it is on this point. The point P is on the first line. And my point is 1, 0, and 0. Now, using this equation, d is equal to the absolute value where A is equal to 1, B is equal to 1, and C is equal to 3, and it's coming from here. So I have 1 multiplied by 1 plus 0 multiplied by 1 plus 0 multiplied by 3. It's a nice point to pick, isn't it? And then it's going to be divided by the square root of 1 plus 1 plus, in this case, is 9. And so my distance between these two parallel planes is going to be 1 over the square root of 11. And that's it. That's this whole video. It's a long one.